Yeah, in the last two videos we talked about measures of central tendency and measures of variability, and also before that we talked about measures of summarizing data graphically. So now we have all the pieces together. So if we have a data set and we want to summarize it, first we do a histogram, we find out the shape of the histogram or the distribution, whether it's bell-shaped or not. Then we find a measure of central tendency, which can be a mean or a median or a mode, and then we find a measure of variability, which can be the range or the variance or standard deviation or mean absolute deviation. But we're going to focus on a few of these. So here is our summary for that. To remind you of what these measures were, the numerical ones. So we have the numerical methods and talk about the summary. So we have a data set. Again, a data set is represented by x1, x2 up to xn. So we have a sample of size n. The measures of central tendency, we have three of them. The sample mean, and today I want to emphasize the word sample. A sample means because it's calculated from a sample, and so the formula for that is x bar equal add all the x values divided by n. The median is the middle number when you arrange the data in ascending order or increasing order of magnitude, and the mode is the one that occurs, the value that occurs with the most frequently. Or if you have a histogram, it's the middle of the middle of the histogram where you have the highest frequency, the middle of the class with the highest frequency. Measures of variability, I want to focus on the range, which is, again, we said it's the max minus the min. The variance, where you take the x minus x bar, that's the deviations, you square them, so that's the squares of the deviations. You add them up together, so that's the sum of squares of deviations. You divide by n minus 1, and that gives you the sample variance. And the sample standard deviation, just simply take the square root of that. So as an exercise, we should find all these measures for the data we had in these notes on the weight loss problem. Now, of course, in general, populations are very large, and you can have sometimes even, like, if I want to find the average age in this country, I would have to check the age of or more than 300 million people, so that's a very large population. In some cases, populations can be also infinite, but in some instances we have small finite populations. And in this class, after I give you the first test and I calculate the mean, or the average, that would be a population average because that's my population. Unless I think of you as a sample for all university students, then it would be a sample mean, but there's no reason to do that. So if you have a small population, then the data you have would be every measurements in that population. So x1, x2, xn. So if I have 20 students in a class and these are their test scores, there would be 20 of these. So if I find the mean, the average, I take all these scores, average them up, divide by 20. That gives me a value called mu, the population mean versus the sample mean. Again, so I'm going to use some Greek notation here again. So that's called mu, and it's written as m mu of mu. Also, if I do the calculation, if I want to find the variance for this data, which is the whole population, I take x minus mu now. So I didn't take x bar because I know what mu is. So it's the deviation from the mean I square the deviations, add them up, and divide by n. My population size, not the sample size. So that gives me the and there's no penalty here. I don't divide by n minus 1 because I knew exactly what the population mean is. The penalty we incurred previously was because we used X bar. So here I get my population variance, and of course I can get my population standard deviation by taking the square root of that quantity. So few reminders of what we do in this class, because we are interested in population parameters. Most often population is extremely large, so we pick a sample that represents the population. Now we haven't talked about what does it mean to represent the population, or except briefly say the sample is random. So if a sample is random and that represents the population, we only calculate measures from the sample. We call them statistics. And this word statistics here means it's the plural of the word statistic. Each one of them is a statistic without the s. So based on what we've done here, our sample statistics are x bar, s squared, and s. Our population parameters are mu, sigma squared, and sigma. So typically these are unknowns, so these values are unknowns, and we calculate these from a sample, and we use these as estimates for these values. Of course, anytime you estimate, you have to tell me how good your estimate is, but that's for later on. So now we're going to talk about, this is very standard deviation is an important measure. So what does that mean? And so I'll talk about the practical significance of the standard deviation. I just want to go briefly, talk briefly about this here, and the Chebyshev inequality, which is regardless of the shape of the frequency distribution, we always have 1 minus 1 over k square of the measurements are within k standard deviations of the mean. I like to restate it in this format because it's much simpler, which means 1 minus 1 over k square observations lie in this interval, x bar minus ks, x bar plus ks. So if I have a sample or a population where I know the mean is 75 and the standard deviation is 6, then I can use this interval here to get if k equal 1, which means within one standard deviation, 1 over 1 minus k squared would be 0. So I know that at least 0 of the measurements would be between 69 and 81. Doesn't tell me much, but it gets better if we go to k equal 2, because it tells me 3/4 of my data is between 63 and 87, and it tells me at least 88% of all grades fall in the interval 57 and 93, and you have question marks here for you to fill out. So I want to show you here graphically on this picture what's going on. So I have here my x bar, which is 75. I know this is not a good quality picture, but you have to bear with me. I have x bar plus s, which is 75 plus 6. Oops. It should be 75 plus 12, 2 standard deviations. Here I have 3 standard deviations. Here I go below 1 standard deviation, so that's 75 minus 6. I have 75 minus 12 here, and then 75 minus 18 should be 75. Let me fix this, 75. And so if my data set is spread around this interval here, based on this Chebyshev rule, it would tell me at least 0% of the measurements are in this interval, not much. But it tells me in this interval from 75 minus 12 to 75 plus 12, which is you've seen it here, 69 to 81, I have 75% of the measurements. And if I go 3 standard deviations, from 3 below to 3 above, I got 88% of the measurements in that interval. So I want you to also extend this to 4 standard deviations and to 5 standard deviations in the homework problem. Because where do we get those numbers? The 0, it comes from 1 minus 1 over k square, and that's, so let me go and get you, show you that. So that's 1 minus 1 over 1, that gives me 0. 1 minus 1 over, and now k equal 2, 1 minus 1 over 4, that's going to give me 75%. And if k is 3, 1 over 3 square is 1 over 9, my 1 minus 1 over 9 gives me the 88%. Again, those numbers here come from, again, these two numbers. So this is 75 minus 6, this is 75 plus 6, this is 75 minus 12, because I get 2 standard deviations, this is 75 plus 12, and this one here is 75 minus 18, or 3 standard deviations, and this is 75 plus 18, or 3 standard deviations. So the question now, what happens if we knew that our data is bell-shaped? So suppose, I'll give you that picture again, and instead of saying I don't know what the graph is, because the graph here, the histogram of the data could have been anything. Now what if my graph is a bell shape, goes up and then goes down like this? What kind of numbers would I get? What can I say about the data? And once you add that new condition, that the frequency distribution is bell-shaped, we can improve those numbers of Chebyshev significantly, and that's what we call the empirical rule, right? And so we're going to talk about that next in the next video. For the time being, thank you.